So thanks for invitation and the introduction. So yeah, I'll be talking about high to low temperature when model at large N. So this is a recent work with Justin, uh, Justin David. So let us just start with a few basics. So if we consider a QFT at finite temperature, we know, first one has to talk about the partition function, right? That is the most basic object. So that should be given by trace over e to the power minus beta h, where beta is the inverse temperature and h is the Hamiltonian in this QFT. So now if I consider a CFT, right, a conformal field theory at finite temperature on S1 times S2. So this is the geometry which I consider. So S1 is because we are studying the theory, the conformal field theory at finite temperature, and in the path integral representation, you know that you have this imaginary or the Euclidean time direction compactified as a length of circle beta, right, which is the inverse temperature, and S2 is a two sphere, so that is the spatial manifold, and that is of radius r. Okay, so this r. And now if we know that if the conformal field theory is at zero temperature and there is and also at infinite volume, so then there is no scale present, no length scale present in the theory. But due to the presence of this finite temperature or the thermal circle and also this finite volume, uh, we uh, we have basically two length scales present in this theory, which is one is the inverse temperature beta and the other is the radius r. And now this partition function, we know that is a dimensionless object, right? So for that reason, this log z, this logarithmic of this z, or the you can talk about the free energy, so that can only be a function of this ratio beta by r, where this ratio is a dimensionless object, right? So I think that is quite simple to understand. And then also this free energy or just log z that admits this high temperature expansion. So high temperature means it's a small beta by r expansion. So this is the expansion it admits formally. So the leading most term will be very familiar to you. So that is you have in the numerator this 4 pi r square. This is just the volume of the sphere S2, and then this inverse temperature square is there. So we know that it has to be a extensive quantity at high temperature, right? So the volume just factors out, and then to make it dimensionless, you need this beta square in the denominator, and c0 is a constant which is specific to a theory. And now this is the leading most term. So there will be corrections because of this finite size effect. So these corrections are in orders of beta by r. Okay, and also there can be a log beta by r term. So you can find similar just from general arguments, these similar expansions are given in these references, although they are not considering the log term, this log beta by r term, because they are restricting themselves with finite gap. It's like finite mass gap, the theories with finite mass gap. But in case of free theories, this logarithm of beta by r might appear in this expansion. Okay, so then just let me show in our case in the large n vector model. So that is and I can readily give you like examples of this kind, right, where such expansions are there. So in this theory itself, so why one of the reason to study this large n vector model at the non-trivial fixed point, yeah, so this is a tractable example of a CFT at finite temperature. Okay, so the partition function both at the Gaussian fixed point as well as the non-trivial fixed point, this non-trivial fixed point is obtained at an infinite coupling, can be computed from the field theory calculations. Okay, it's completely from the field theoretic side calculation, like a CFT calculation. So in the Gaussian fixed point, this expansion looks like this, and at the non-trivial fixed point, this is the structure. Okay, so now also let me define a ratio of the log z at the non-trivial fixed point. divided by log z at the Gaussian fixed point. Okay, so this ratio should also be a function of this beta by r, as both the numerator and the denominator are function of beta by r. So then we can take this beta by r, I mean then at the limit where it is at strictly at high temperature, so the beta by r goes to 0, that can be evaluated just from the leading most term, right? That is the leading most term gives you the strict uh, beta going to, I mean beta by r going to 0 limit, okay, or the high temperature, strict high temperature limit. So that can be just evaluated from this C0, okay. And now I mean, for example, in n equal to 4 super Young-Mills theory, this ratio at this limit beta by r going to 0 is evaluated to be 3 by 4, and in the strong coupling limit you have to take help from the holography. So then let's go back to our model in the Wayne model. So in the Wayne model also, this ratio at the strict high temperature limit, it has been found to be 4 by 5. Okay, so which is very trivial from here. So you can just look at the leading most term from this equation 4 and equation 5, and you can take the ratio, and it comes out to be 4 by 5. So now let me just pose the question which we are going to answer in this talk. So can we find this ratio for the theory of Wayne model on S1 times S2, right? So means, I mean, in this case, we are taking the strict the high temperature limit. So that means we are almost going to the limit where it is S1 times R2, right? So where just the leading most term is considered and all the rest of the terms are neglected, okay? So now the question is, can we find this as a, I mean, this ratio as a function of beta by r? So for any, and how does it behave, this function behave across various values of beta by r, okay? Across for arbitrary value of beta by r. Okay, so then to answer that question or to evaluate this ratio for all values of beta by r, one needs to compute the partition function at the non-trivial fixed point as well as the Gaussian fixed point. But finding an analytic answer for all values of beta by r is difficult. Okay, so analytic answer is difficult, and but what do we have in our hand? So in our hand we have we have found the partition function at high temperature as a order by order expansion in small beta by r. Okay, so there are higher order terms which also we have evaluated. For illustration, we are not showing all the orders here, uh, and yeah. So uh, then another thing which we have in our hand is that, I mean, which we obtain in this current work. So I should mention that this result was obtained in a earlier work from the last year. And then also another point which we have is the low temperature limit. At the low temperature limit, I mean, we can find the partition function as an expansion, order by order expansion in e to the power minus beta by r. Okay, so the expansion is in terms of exponential, basically e to the power minus beta by 2r. So where this log z free, this first term is basically the logarithm of the free partition function for a conformal scalar on S1 times S2. Okay, so one point I should note here is that if you look at the leading most term in this low temperature expansion, then the most leading term will come from this log z free. Okay, when you put n equal to 1 and l equal to 0, so then it is just n beta by 2r, right? So that is the leading most term. So basically, I mean, what I mean to say is that this log z at the non-trivial fixed point, as a low temperature expansion, the leading at the leading order, it just resembles the free theory. Okay, at only the leading order. But if you go higher order, then it is certainly different. Okay, so then I asked that whether we can calculate this ratio, the ratio of the partition function at the non-trivial fixed point divided by the free or the Gaussian fixed point for any arbitrary value of beta by r. So I mean, yes, we have calculated that, and it is plotted here. So this is the ratio, this log z at the non-trivial fixed point by the free fixed point. And then if I start explaining from this figure B, so we have seen that like at the strict beta by r going to 0 limit or the high temperature limit, it was the value was 4 by 5, right? So 4 by 5 means this 0.8. So then if I go increase this beta by r, then I mean the nature comes out to be, nature of this function comes out to be, it attains a minima. Okay, it decreases from this value and it attains a minima, and then it increases. Okay, and this is obtained by a Borel-Padé resummation numerical technique of the high temperature expansion. Okay, so and this graph in the figure A, this is just the direct plot of the low temperature expansion till this order. Okay, so from this you can see it, I mean similar structure is also there, like it attains a minima here around this around some value which is 1.517. Okay, and then it increases, and it goes to 1 finally when it beta by r is going to very very large, so it goes to 1. So that is also, I mean the reason is here,
Sorry,
right?
can I ask something?
Yeah, sure.
What's the difference between these two graphs again?
Yeah, I mean the difference between the graphs are one. I mean they are obtained from different side. Means like we have basically we have the low and the high temperature, right? I mean this is the high temperature expansion, and this is the low temperature expansion.
So all of
So
this, both formulas. So you have the
yeah,
Gaussian and non-trivial fixed points.
right.
And
So yeah, I'm sorry. Just let me explain it again. So I mean we are looking at the. I mean we have in our hand both at low temperature and the high temperature. Sorry, these are like these are the high temperature expansion at the Gaussian fixed point as well as the non-trivial fixed point, right? So I mean this is the high temperature expansion of at both the points, and also we know at low as a low temperature expansion, we know the Gaussian fixed point, which is just this log z free is the Gaussian fixed point, the expansion of that, and this is the non-trivial fixed point. Okay, so now like in principle as an expansion in the both the sides, like as a high temperature expansion and low temperature expansion, you can find out the ratio, right? So then, I mean, but how to evaluate it for a all or finite beta by r? Okay. So in one side it is beta by r going to 0. Like in this side, like let's say in this graph, this side we in a
sorry, when I look at the left graph, when you say
yeah
it's low temperature expansion, so
right,
I should be looking at large beta, right?
right. So I mean this.
So why does it make sense for small beta?
Yeah, I mean it is in small beta, it should be, it's not be, it will not be a very good approximation, but in this region it should be a very good approximation.
Yeah, but it looks like
But
it is a good approximation for small beta. It looks like it goes to 0.8 for small beta. How do you explain
no, I don't show it like after this. Actually it has errors. I mean I will show that
Well, it
the more
goes very
graphs.
close to beta over r equals 0, and it goes to the right values.
Yeah,
I don't
yeah,
understand your graph.
no, sorry, I mean this is from the low temperature expansion.
Yeah, so
And
it means
it
sorry, I'm
Mhm.
sorry. What
Yeah,
I
it's
don't
fine.
let me just repeat.
Yeah,
So from what you're saying, the left graph you should trust for large beta over r,
right.
but it looks like it's good all the way to small beta over r. Why?
Yeah, I mean like it's somehow in this region, like when you are not very, this is like some, let's say 1 or something. Okay, so at that region you can see that there is a similar nature you can see. But if I mean I have checked that if you go smaller and smaller in this like near 0, then certainly it doesn't go to 0.80. It in fact grows, like I mean it becomes very different.
But isn't it surprising that even the way it looks like it goes very
Yeah,
close to 0.8?
yeah. So I mean, I think it will be like although in this region it might be. I don't know if it is surprising or not, but it has some. I mean, it's not exactly matching. So here I mentioned the point that you have this. I mean, the minima, the value at the minima is 0.76 from this high temperature expansion. So this is like supposed to be, I mean, a better approximation, and the value at the minima is attained is 1.5 this. Okay, and
Yeah.
but if you just look at the low temperature expansion just directly from the low temperature expansion, then if you really evaluate these values, then they differ by 10% and 0.5% from these values.
No, it's
Okay.
still amazingly close.
Yeah,
Yeah.
I mean it might be I don't know, like if this is not very I mean, in this region, still it is, yeah, reproducing similar result, right?
Okay, thank you.
Yeah, but yeah, yeah, sure. Yeah, I mean, it's like, yeah, you're, I mean, what I understood from your question is that you are telling that, I mean, this ON model is like a free scalar plus, I mean, a mass, right? So there, I mean, yeah, we have presented some analytic, in fact, some analytic expression, I mean, analytic tool to show that high temperature and low temperature expansions are same. And I mean, without using the knowledge of the gap equation, right? So, I mean, here the knowledge of the gap equation is still also being used, right? So in that case, you do not have any analytic tool to show their equivalence, or I mean, or if I tell you to find the partition function for finite beta by r, you do not have any analytic tool. Does that, I mean, make sense to your question? Uh, yeah, I couldn't fully get the question although, but okay. Okay, fine. I think it will be clearer if I go ahead. I mean, I just wanted to show you the result first, so that you get some idea in the beginning that what I am going to talk about. So, okay. So, yeah, so the point is that, I mean, yeah, it's still from both the sides, you can see a similar nature from this plot. Okay. I mean, one point I can mention that in this case, like the question which was asked, that why it is, I mean, this low temperature expansion is still giving a quite a, I mean, can capture the behavior at a high temperature limit. It can be because of, I mean, this is a exponentially suppressed. I mean, the series, the terms are exponentially suppressed. So maybe, I mean, even in that limit, so it works out. Okay, at this approximately it works out. Okay, so now a couple of general motivation in this, I mean, why should I study this model? So, or this overall study. So the study of the conformal field theories on S1 times S2 are important in the context of ADS CFT with black holes in the bulk, and also as a study of quantum field theory on card background at finite temperature. Our study presented neat calculation by implementing large and simplification on the ON model. So now, to give a, I mean, like, feel about what we are going to do, and I mean, or what is the actual motivation, then, I mean, we start with the free CFT on S1 times S2. Okay. So these are like the result I am going to show, those are like quite well established, but I think it will be useful for our discussion of the ON model. So, I mean, here I consider this action. So in this action, I mean, you have this curvature coupling or the conformal coupling, where R is the Ricci scalar, and it is 2 by r square for a two sphere. Okay. So then, I mean, then what we are going to do is that we evaluate the partition function or the logarithm of the partition function as a small beta by r expansion, which is the sorry, a large beta by r expansion, which is the high temperature expansion. And then we'll show that low temperature expansion, that expansion can be resummed to obtain the high temperature expansion from that. Okay, so that is the goal of this section. So you have this path integral for the partition function, and this is your geometry. So and you know that you have a periodicity in the Euclidean time direction. So theta phi are the angular directions. Okay. So then we just use this mode expansion, just the conventional way. So n is the Matsugaru frequencies and YLMs are spherical harmonics. Okay. So then you can perform the path integral by integrating over these modes A, N, L, M, which is this. Okay. So then I mean, I think you can just sum over this Matsuburg frequencies n, which is quite a standard trick in the thermal field theory books or something. So then you can do that sum over n and you obtain this result. Okay. So now I should mention that the first term, which is given in red, so that is a diverging object, right? So sum over L is diverging. So we have to regularize this term. So we regulate this sum by using the zeta function regularization, and we just put s equal to minus f finally, and that in that analytic continuation it is 0. Okay. So the first term vanishes. So then we are left with this term. So this term, I mean, as I told you, we are going to study this at as a low temperature limit. So where beta by r is large. So that means this, I can consider this e to the power this object to be x, and that is small. So I can expand this log 1 minus x in a small x expansion, right? So that leads to this result. So this is the low temperature expansion of this log z on s1 times s2. Okay. So then I'm going to show how to reproduce the high temperature expansion of this free theory uh, just by resumming this. So the method was given by Cardy, okay, in 1991. So you just represent this exponential, you can represent this exponential minus t as a inverse Mellin transform of gamma function, which is this. Okay. So then, I mean, you have to choose the contour in such a way that it contains all the poles of this gamma. So A has to be, I mean, A should be chosen so that it is like in the right side of the imaginary axis. Okay. So then we just use, I mean, for each of the exponentials which are occurring in this equation, uh, we we just use this representation. Okay. So and we obtain this. We just plug it here. uh, I mean, yeah. So then you can do the sum over L and N, and that gives you these zetas, and yeah, these zeta functions basically. So then in the final step, you have to do this integral. So this integral can be evaluated by Cauchy-Residue theorem. So you can look at the poles of the integrand. So I mean, you have, I mean, for s being negative integers, there are poles because of this gamma function, and then s being 0, there are one double pole as well as a single pole because of, I mean, this zetas, and also, I mean, at s equal to 2 there will be a simple pole. Okay. So uh, sorry. So yeah, so that is what I mention it here. And then you can evaluate these residues at s equal to 2 separately and s equal to 0. And then also I evaluate at s equal to n. I mean, n is some negative integer, any negative integer. So we just finally combine all these effects of all these residues, and to obtain this log z free as a high temperature expansion. So this exactly reproduces the high temperature expansion. So this is the scenario in the free theory, the Gaussian fixed point. So you can start from the low temperature expansion, and you can directly land up into the high temperature expansion by a resummation of the series. So, and this result has also been reproduced in a different approach. I mean, not using the low temperature expansion, but from small beta by r expansion of the free energy of a massive scalar by taking a massless limit. Okay. Thus, we have reviewed this Cardy's
Sorry,
method.
can I ask you
Sure.
something? So what's the
Sure.
radius of convergence? So of these expansions?
Okay. So no, this you are asking the high temperature or
Well,
this or
both.
the other?
I think you start with one and you get the other one. So
I start with this, right? I start with this expansion,
yeah.
and then I obtain the other one, this one.
So what's the radius of convergence of both of them?
I mean, this radius of convergence for this series, I think this, I mean, if you just open this up, I mean, and then you will see that this is also an asymptotic series. So
So both of them asymptotic series?
Yeah.
So how did you get, like,
Yeah, I mean, yeah,
what's the magic here?
yeah, I mean, here you have some analytic control, right? So you can use such analytic tools, and you can show that they are equal.
Well,
But
they're equal in a formal way. I mean, you could have gotten some
yeah,
other asymptotic series somehow.
No, I mean there are like I think there are many other ways to show their
Sorry,
consistency.
but I
Hmm.
don't understand what's happening. So you have some asymptotic series around zero and some asymptotic series around infinity. How do you get one from the other? Like presumably you can get some other asymptotic series depending on analytic continuation. No, you do some analytic
Yeah,
continuation presumably.
yeah, I think these are, yeah, there are anti-condition involved, but I think you can use, just like this, you can evaluate, this is another way of obtaining the high temperature expansion, not using the low temperature expansion, okay? So you just, use a massive scalar, okay?
I understand.
Mhm.
You can presumably you can. There is a correct result, but actually,
I mean,
why is it an asymptotic series?
if you write it up, then
Is there a
it is an,
physics reason?
uh, physics reason, I'm not sure if there is. I can mention some physics
Is
reason
it the
in
same?
this.
Like perturbation theory in QFT is an asymptotic expansion. Is it the same
Hmm.
argument?
Sorry, I didn't hear that properly. So,
Like people argue that perturbation theory in quantum field theory is an asymptotic
yeah,
series. Is it the same
uh,
argument here?
yeah. It is it is a perturbative expansion in beta by r, right? It's a high temperature expansion, you can say, and it happens to be an asymptotic series.
Mm.
It is a like it's not a perturbative expansion around the coupling constant or something, but it is the perturbative expansion of your partition function or the free energy in a as an expansion in beta by
The
r.
question was why was it an asymptotic series instead
Yeah,
of having some finite radius of convergence?
yeah, I'm not sure if there is any a priori reason I can tell you. Okay, but maybe if something comes into
Mm.
my mind in the due time, I'll tell.
But I should think of this matching as some kind of trick when you go
Yeah,
from low temperature to high temperature.
right.
And okay, thanks.
Well, it
Yeah.
probably, sorry to interrupt, it probably means that this particular analytic continuation you're doing is the meaningful, is the correct one, so to speak, no?
That's right.
That's what you...
Yeah. One has
Yeah.
to stick to that because from just like I said, like there are other checks for that.
Mhm.
So in a different way you go and you get the same result. So that means you have to stick to that analytic
Yeah.
continuation.
Uh-huh.
You're right. Yeah.
Sorry, can I just ask or comment? I think the low temperature expansion is convergent. The high temperature expansion is asymptotic.
I think low temperature expansion is also very involved in that sense. Well, wait. In the free theory, this is just this, right?
In the free
Uh,
theory.
yeah, in the free theory, so it is an like exponentially suppressed term, but you are I cannot surely say that if this like if you write down the term by term, so then you have this 12 plus 1 upstairs, right?
Mm-hmm.
In the definition of the asymptotic series, you might have this like a growing factor here. It's not factorially growing, but it can, the coefficients here can be increasing,
Oh,
right?
okay. Okay. Yeah.
But can be
Thanks.
not asymptotic, but just have a finite radius of convergence, right?
Yeah, it can be. Okay, so I'm not. I was like mentioning the final result. Like in the non-trivial fixed point, it will happen to be that like both sides are asymptotic series. But in this case, I think it is fine still. Yeah, at least you can do the. You have to do. Okay, why I need such trick in this sense is that if you want to sum it over, you will hit various singularities. Okay, if you want to sum this series, so then you will do this sum over L. So sum over L if you do, then finally you will go in such a region where some zeta one kind of a log kind of divergence will appear. Okay, so to remove that log divergence, you have to use some sort of like just like we have done a massive scalar, we have considered a massive scalar, and finally carefully we have taken that mass to 0 so that all the divergence are gone. And this way, this Curtis method, this like automatically avoids that kind of divergences, and it lands up into the same result. Yeah. Sorry. Hello. Is this fine?
Yes.
Yeah, thank you.
Yeah. So, okay, let me just go ahead. Okay. So then, yeah, we have, I mean, at least for the free theory, we have this control. And then let's ask the question, like, how can we find a method to reproduce the high temperature expansion from the low temperature expansion, or vice versa, at the non-trivial fixed point of the ON model on S1 times S2, okay? So, I mean, and in that case, you have no, I mean, at least to our knowledge, there is no analytical control. So now if the answer is yes, if we can do something, then does the method allow us to study the ratio for all values of beta by R, okay? So that is the original question. And then we just go into this model. So along with this part which appeared, I mean, in the first two terms, which appeared in the free theory as well. So this term is like quartic interaction, and you have a solvable limit at n going to infinity. So then, I mean, we just have to evaluate this path integral. So then we use the standard trick of Haber-Stratton transformation. So, I mean, you just represent the quartic interaction term in terms of this path integral, in the auxiliary field zeta. So it's just a Gaussian integral. So you can do it, and you can get back the phi to the power phi I squared, like quartic interaction term. Okay, so that is, and then we separate the zero mode and the non-zero mode of the auxiliary field zeta. So zeta naught is the zero mode, while zeta tilde is the non-zero mode. And then at the leading order in large n, only the zero mode of the auxiliary field survives, and it plays the role of a mass in the action. And then the contribution due to the non-zero mode arise in the systematic corrections, which are suppressed in large n. So in our work, we only focus on the leading order in large n. So the non-zero mode will not occur in our study. Okay. So then, yeah, then we just evaluate the path integral, and we can find this z tilde, the partition function, to be this, where this log z, this part you can think of a massive, I mean, partition function of a massive scalar, as it was asked. So m tilde square is I zeta naught. So m tilde, like this mass is related to the zero mode of the field, zero mode of the auxiliary field. So then we have to, like, finally what we will do is that we just evaluate the saddle point of this integral. Okay, so evaluate this integral using the saddle point approximation, and then yeah, then what we and also, I mean, the saddle point, we take the lambda going to infinity limit. So this term basically drops off. Okay, so yeah, so then I mean, then before going into like the saddle point analysis, first we have to evaluate this log z part. So which was this, just the massive part, right? So you can do this sum over n, the Matsubara frequency, in a very similar way as the free theory. It's just a textbook kind of technique, and we can evaluate this. Okay, so then we define the first term to be log z1 and the second term to be log z2. So and I can say that this above expression is not known to admit a closed form representation in general, but as a high temperature expansion, we have obtained this, I mean, this quantity, this log z, as this series expansion in terms of small beta by R expansion. So this was the result at the high temperature expansion, although I am not giving the details in the high temperature expansion. I think sometime Justin had talked about this in this same seminar series. So then if you can just evaluate the saddle point condition, which is the differentiation with respect to m tilde is going to 0. So that equation is this. It just comes out to be this, and then you can solve this m tilde from this equation. Okay, and this m tilde is an order by order expansion in beta by R, and we have many higher order terms in this. So then I mean, you can just use this result of m tilde into the partition function, and you can use the, I mean, you can evaluate this log z, as a series expansion in small beta by r. So these are like finite size corrections. And also you can find the energy density and so on. Okay. So, and also one can check that stress tensor is stressless using this log z. Okay. So in each perturbative orders in beta by r. So that just confirms the conformality of this model. So then in this work, in this current work, we also find a low temperature expansion. We just, okay, let me just go back a little bit. So to the definition, I mean, I want to remind you this definition. So we just take up the first term, the log z1, okay. So this is also a diverging object because there is square root upstairs and this sum over L is diverging. So I have to use some regulator, right? So yeah. So I just call it, I mean, I just use this alpha. So I instead of square root, I just make it minus alpha. So if alpha is greater than 1, then it is a converging object. And then what you do is that you just use a integral representation of this object with the power minus alpha, and then we are trying to find the large beta by r expansion, which is the low temperature expansion. So in that context, this m tilde beta, if I mean we can consider m tilde beta to be finite, because that is the thermal mass. So m tilde beta, if you consider like these two terms and compare them, so m tilde beta should be some finite object, while this beta by r is large. Okay, so that means, I mean, you can consider this to be a small quantity and you can expand in small m tilde beta. This exponential you can expand in small m tilde beta, and I mean basically this m square is less than 1 by 4 r square is the condition for that. So I mean, even if L is the like the smallest value of this quantity, which is this first term in the exponent of the exponential, so the smallest value is L equal to 0, so that is 1 by 4. So it's like beta square by 4 r square is there. So m tilde beta is even smaller than this 1 by 4 r square. Then we can expand this m tilde beta as a small expansion, right? So I mean as a small expansion in m tilde beta. So that's what we do, and then we are left with this integral. So we can perform this integral, and in the final result we just put alpha equal to minus half. That is the analytic continuation we are using, right? So then we can perform the sum over L from 0 to infinity, and we can get this result. Okay, so then in this result you can note that it starts from n equal to 2 to infinity, because
Sorry, I'm a bit confused. So until the maybe smaller than 1 over 2r, but it's roughly of the same order. It scales like 1 over r. So you're expanding in something which behaves like beta over r, but beta over r goes to infinity. So I find it a bit confusing.
Beta over r is very large, right?
Well, that's
so
exactly what I'm saying. So you're expanding. So your m times beta is roughly beta over r, which is very large, but you're expanding in it. So
no. M tilde beta is like I mean you can just take it to be finite object. So then if you take that beta by r common, so it will be like r by beta order, right? So then you can expand it. I mean, this object is very large and this is finite. So you can take this beta by r just outside.
Why is it finite?
I mean, yeah, you should expect this is a mass, right? Mass.
Actually, you say this thermal mass is roughly like 1 over beta. That's what you're saying.
I mean,
right.
Yeah, certainly. I mean, it's a conformal field.
Right.
I mean, to have a conformal field at finite temperature, m tilde beta is some finite order, like order 1 or something. I mean, at least it shouldn't be of this beta by r. Okay, fine. Yeah, can I go ahead? Yeah. So so then we just use that analytic continuation, and then you can see that this n equal to 0 and n equal to 1 term, they just vanish because of the sum over L. Okay, so that's what we obtain. So this is the result for the log z1, and then we have to evaluate the log z2, the second term. So this is I mean, this was just this. So again we use some integral representation of this exponential for this exponential, and again we use the similar trick. So like m tilde beta is finite, and you can consider in this exponential there is a small object compared to the other one, so you can expand in small m beta by r in that sense, right? So then you can integrate this tau integral, and you will obtain this modified Bessel function. So now this modified Bessel function is of order half integer order, right? So because p is equal to integer values, so p minus half is some half integer. So this always admits some truncating series representation till some finite number of terms, right? So then thus we obtain the there is a small r by beta expansion for this log z, right? I mean, we just combine the log z1. So log z1 was also a r by beta kind of expansion, okay? And then this is also log z2 is also r by beta kind of expansion with some exponential suppression, okay? So which is this e to the power minus beta by r, and then we can just combine them, log z1 and log z2, to find the log z, and then we can evaluate the gap equation or the saddle point condition by this, and it turns out to be this equation. The saddle point equation turns out to be this, and finally you can solve this equation to obtain the thermal mass to be this, okay? So yeah, as it was, I mean, anticipated, this AMR comes out to be some object which is exponentially small. Well, so then we can, I mean, you can just make a consistency, I mean, or the region of validity of this low temperature you can find by using, I mean, we have used this sort of condition, and then you can just take the leading most term and you can put it here, okay? And that will lead to this condition that beta by r is greater than this 2 log 32 by pi square. So that is in this region, if beta by is greater than this value, then this is a meaningful object, or this is a consistent expansion for the thermal mass from a starting point, right? So then we can again substitute the thermal mass in the partition function, and we can evaluate the partition function or the log of partition function. So that leads to this expansion, and this log z free is this, okay? So then you can again evaluate the energy.
So what happens at the critical value?
At the critical value,
given back
this
by 51,
beta by r equal to this, okay?
Yes.
So I think, I mean, it won't be like if you go in the other side, it's like it's making more erroneous or something, right? I mean, error will be higher and higher. Like this is not a good expansion. I mean,
well, so is that like, is it where, like, I would think that that's where the radius of convergence happens. But
yeah, you can say in that sense, like, I mean, it's
but
like
I thought you were telling me that it's all asymptotic, so I'm a bit confused.
I mean, okay, this condition is saying that where this derivation is consistent, right? I mean, the derivation I am doing from here, like I am expanding the small m and all. So in what region those are consistent? That is what I am that is what this beta by r greater than this value says.
Yeah.
Yeah, I mean, I don't know if you can say directly that this is a radius of convergence exactly. I'm not sure about that.
Well, I thought your claim was that the series was asymptotic.
No. I mean, sorry. I mean, the series is asymptotic. Yeah, that can be. But the point is, I mean, this is not the radius of convergence as such. Okay. So this is just the consistency.
Well, if the series is asymptotic, then it's better not be the radius of convergence, right?
Yeah, there shouldn't be any radius of convergence, but it is like if you are going away from this region, it's less than that, then what I mean is that this derivation is not a complete object, right? That's what I mean. I mean, you should trust this expansion. I mean, from the gap equation as a solution of this gap equation. You can trust this expansion when beta by r is greater than this value. That's what I mean. Okay. Is that fine? Okay. So yeah, let me just go ahead. So then I find this log z as an expansion in e to the power minus beta by r, and then then how to show the equivalence between the two expansions, that one is at high temperature and another is low temperature, and these are computed independently, right? I mean, without using the knowledge of the low temperature, we are not using the high temperatures, like not like that. So
sorry,
the
before
method,
you go there, can I just ask, you have this polynomial thing, the terms in beta. if I think about the character decomposition and the spectrum is half integers, how do they appear?
I'm sorry.
I think
This
if we do character decomposition, we can only get polynomials in e to minus beta.
This
in the partition function. In the partition function. Yeah.
This is not character decom. This is not. I'm sorry, I'm not.
The one later with Z.
Okay. This right?
One. Yes.
Okay. Yeah. Okay. This is not. I'm not saying this is character decomposition. It can be cast into some kind of decomposition, but it is just some like meaningful series in large beta by R. That's what I am saying.
Yeah, I understand, but it's not even it seems not to be decomposable. I mean, if the spectrum is half integers.
If the spectrum is half integers, I mean, because it is a beta by R e to the power minus beta by R kind of expansion, right?
Yeah, basically the characters are all polynomials in exponentials, so I cannot decompose beta, for example, in characters.
I mean, okay, the characters you can think of in the Z, right, in the partition function. So it is a logarithm log of Z. So in that it might appear. I mean, the character decomposition is for the partition function itself.
I agree, but even if I exponentiate this, I would still, I think.
I mean, yeah, it's basically you have to. Yeah. I mean, this point I thought about. I mean, earlier that I mean it's it can be so that such a function that it will, if you take the log, it is not always a simple. I mean, and expand it, it should not hold the similar structure as the character decomposition. Okay.
Okay, thanks.
Yeah. I mean, it is one comment I can say in this point. Like, it will be interesting to decompose this object in terms of like, okay, some sort of other characters. Like in you can evaluate the stress tensor, the 0,0 component of the stress tensor, and then one should try to decompose in terms of conformal characters. Yeah. I mean, not conformal characters. It's like conformal. I mean, blocks. Sorry, not the conformal characters. Conformal characters you can only think of in the partition function itself, not the logarithm. Okay. So then yeah, how to show the equivalence between these two expansion? One is at high temperature and the other is low temperature. So the method is going to be Padé-Borel sum of the high temperature expansion. And we'll use this to extrapolate to lower values of the temperature and show its agreement with the low temperature expansion. Okay, so then then I want to mention this partition function, or the log of the partition function, till a very high order terms, right? So like beta by R to the power 34. So if you just go ahead and you can see that first these coefficients are decaying or decreasing, then from this point, like after order 8 term, it just starts increasing, and it's after that it just rapidly increases. Okay, so this series is an asymptotic series, and one has to handle this with some care. And so for that we use this method of Borel-Padé. So I'll just outline the method in a very simple terms. So let us just consider this fx as some asymptotic series where n grows factorially with n, and it can, I mean, there is no radius of convergence is 0, and it can approximate the function only in a region very, very close to x going to 0. So then for that, what we do is that we first do the Borel transform of the series. So we divide each term by n factorial to remove the factorial growth of this n. And finally, one can formally write down this fx back in terms of the Laplace transform of this Borel transform. Okay, so, and that, I mean, if you do this integral, it will cancel this n factorial. So that's how you rewrite the fx in terms of the Laplace transform. And it's just a simple example for this series. So you first divide by n factorial, and then you can just sum over this n equal to 0 to infinity. and you can get this back, right? This 1 by 1 minus x. And finally you have to do the Laplace transform. But in the Laplace transform, you can see that this t there is a pole in t equal to 1 by x, right? So to avoid that pole, I mean that pole actually obstructs your contour from 0 to infinity. So to avoid that pole, we are taking principal value prescription, and that will reproduce this answer, this exponential integral. So any other choice of the contour will lead to an answer with the with a non-zero imaginary part. So we know that we start with a series which is real. So we want to get this answer. And but in many examples in physics, the asymptotic series only known till a finite number of terms, and still we have to find its behavior away from x equal to 0. So that is exactly the case in our situation. Like you have only like some, let's say, order 34 kind of term, x to the beta by r to the power 34, and from that you have to approximate the function away from x equal to 0 or beta by r equal to 0 whatsoever. So the series representation of course fails, and we need a method that can approximate the function just from a finite number of terms of the asymptotic series. Okay, so let us consider this example where fx is just known up to this n number of terms, and there are higher order terms but which we have no idea, which we are not we don't know the coefficients, and that is out of our knowledge, right? So then again, to remove the and this n just grows with factorially with n as n goes to capital N. So we remove this n factorial growth by dividing it by n factorial, which is the Borel transform. So we take the Borel transform, and then in this step, like unlike the example of exponential integral, we cannot find a closed form expression of this series, as only a finite number of terms are known in the infinite series, right? We cannot just sum it to 1 by 1 minus x, which was shown here. So we cannot do that because we do not know it till infinity. So it is just up to finite n, we know. So what we do is that at that stage, to give it to a closed form expression for this Borel transform series, we use the Padé approximation of that. So we just approximate it in terms of a order p polynomial. And a q of degree q polynomial, and where p plus q is n, and then such that this Padé approximation of this Borel transform should be equal to the Borel transform up to orders of x to the power n plus 1. Okay, so then you can just rewrite this polynomial by polynomial structure into these partial fractions, where this xi and ci can be any complex number, and c0 prime is a real number. So then finally, again, you have to do the Laplace transform. So the Laplace transform is fine when you are doing, when these xi's are not on the real axis, so you can just directly do the integral. So there is no pole obstructing the 0 to infinity integral. But if there are poles on the real axis, real positive axis, sorry, so then that will obstruct this contour, and you have to take this principal value prescription. And now I should mention that the correct prescription to avoid the poles on the positive real axis in the t-plane should be chosen based on the specific asymptotic series one starts with. But for our case, the principal value prescription is correct choice as it keeps the free energies real valued, and result is unambiguous in the final answer. Okay, so we need real valued answer. So yeah, so finally, just combining everything, this is the Borel transform. You can write down the Borel transform in this manner. And then as we already have seen, for the free theory, we have some analytic handle to show that the low temperature expansion can be resummed back to high temperature expansion. So then first we will apply this method for the free theory, means the Gaussian fixed point, and then we'll go ahead to the critical ON model, right? So this is the Gaussian fixed point. So this I don't know if it is visible. Let me just zoom it a little bit. So yeah, so the blue curve, that is the direct low temperature expansion. Okay, that's just the low temperature expansion, and the orange curve is the Padé-Borel resummed high temperature expansion. Okay, so they are agreeing or overlapping on each other for a finite region of beta by r. So you can see these are for different higher order Padé approximation. Okay, so and if you just increase the order, the region of overlap increases, and then if you go, this Padé-Borel resummation, this numerical technique, this has some sort of limitation. So like if you increase beta by r very high, then it should not, I mean, it should not work out. So that's what is being shown here. So for that you have to increase the order of Padé. So then it becomes better and better. So then also I mean, also this question was asked like whether at height, I mean at low temperature, so this blue curve is the low temperature expansion. So that should not be a very good approximation when you go in this side, like in a smaller values of beta by r. So that is being shown in this I mean the curves inside the boxes. So these two curves are diverging away from each other when you are going in the smaller value of beta by r region. So this is the like magnified version, I mean part of this small beta by r region. Okay, so and but yeah, but you can see quite a nice overlap between these graphs in a like in quite a large region of beta by r. So that supports the fact that they are actually representing the same function, or they are just the two different asymptotics of the same function. Okay, so then you can also look at the energy, I mean the thermal expectation of the energy, and there also you can see the similar pattern and the overlap. And finally, this is the non-trivial fixed point. So here also, if you, I mean, this orange curve gives you the Padé-Borel resummed high temperature expansion, and the blue curve is just the plot of the low temperature expansion. So then yeah, then you can see that if you go higher and higher order Padé, so there are overlaps, and they are, I mean, at least in the approximate sense, they are giving you the, I mean, or supporting the fact that they're just the asymptotics of the same function. I mean, just high temperature and low temperature asymptotics of the same functions in terms of beta by r. So then yeah, then you can see that also for the energy similar behavior is happening. So then yeah, and then I should just go back, I mean I use these results or the data in these cars to evaluate this ratio which has been shown here. Okay, so yeah, so I mean, it's just the fact that the question which was been asked, like the series in e to the power, I mean, in the low temperature expansion, so that is an exponentially suppressed expansion. So it is of such a nature that it can still, I mean, correctly reproduce it in also a smaller value of beta by bar. But if you really explore the region in a small, very small beta by r, that certainly fails. That I have checked. Okay, so that's how we finally get this ratio, which was the answer, I mean, which was the claim in the beginning. So we find this ratio, and this ratio looks like, I mean, it hits the minima and then it increases to 1. Okay, so then yeah, so these are the curves, and then I'll just end with some summary and some a few future directions. So we have evaluated the free energy and the thermal expectation of the energy for the Wien model at large n without the singlet constraint on its one times S2 at the non-trivial fixed point as a low temperature expansion. So the free energy in this low temperature expansion has this, I mean, in the leading order, it just coincides with the leading term of a free CFT on S1 times S2. So, and also just a comment in this that it would be interesting to express this in terms of conformal blocks. I mean, it can be, yeah, it can be indeed possible, but yeah, one has to study that. Then we have used the Borel-Padé resummation technique to demonstrate that the low temperature expansion for the free energy and the thermal expectation energy obtained here, and their high temperature expansions obtained earlier in our earlier work correspond to the same fixed point of the model. And also as a highlight of our work, we have investigated the ratio of the free energies of the interacting theory to that of the free theory at all temperatures or for all values of beta by r. And we see that this ratio, I mean, when the temperature is infinity, it begins with this well-known value of 4 by 5, and then it decreases to a minima at 0.76 at this value of beta by r, and then it starts to increase again. And finally, it hits 1, right, at asymptotic regions to unity as the temperature is dialed to 0. So it will be interesting to generalize this study to vector models with other potential, and one such example might be some 5-6 kind of interaction, or also models with fermions. So it will be interesting to study if there is also similar minima is happening. Okay, so then for future directions, the study of weight model with singlet constant on S1 times S2. So so far we didn't put the singlet constant. So it is also interesting to study with the singlet constant, as it is particularly interesting this theory is to be dual to higher spin gravity in ADS4. So, and this model also shows, undergoes the gross Witten-Wadia transition at a temperature which scales like square root n, and in units of radius of S2, and the coupling constant scales like in this manner, where b and lambda are numerical constant. So these constants are determined by solving the gap equation, as well as the condition for vanishing un holonomy eigenvalue density simultaneously, and then it will be an interesting study to find the finite size correction to this transition temperature, as well as the partition function at the non-trivial fixed point of this model with the singlet constant. So, and then another future direction is that we have evaluated thermal one-point functions for higher spin currents for this model, wind model, without the singlet constant on this geometry of S1 times S2. And we had an interesting observation that at large spin limit, this thermal one-point functions at the non-trivial fixed point tends to the answer for the Gaussian fixed point. Okay, so now an interesting direction would be to evaluate these thermal one-point functions as a low temperature expansion and test if the large spin behavior remains universal across the temperature. And finally, also I just want to mention another point: this study of wind model for finite finite temperature. Sorry, this is for finite n I am talking about, and one can use or one can look to develop the setup of thermal bootstrap in this geometry. Okay, thank you for the attention.